All right, and today we're gonna attempt to look at two sections today, section 4.3 and section 4.4. I'm gonna go into the lecture notes section and we're gonna take a look at, I believe it's section 10.6. And I'm also going to bring up the unit circle. I'm going to go and form the sheets, and I'm going to bring up the unit circle. All right, and I believe the last time we left off, I believe we had finished the law of cosines. We kind of talked about the ambiguous case, and then I believe we went into section 4.3, which was polar coordinates. Okay. All right, and I'm going to just bring up the 10.6 set of notes, which is here. All right, and we're going to talk about polar equations and polar graphs. Okay, so the last time I really didn't go into detail about the actual setup. We just sort of looked at a polar graph and we plotted a couple of points. But here is the polar coordinate system in more detail. And we have two coordinate systems thus far. We have the rectangular coordinate system, which is, I'm just going to pull up a Google image. Okay, the rectangular coordinate system, and which is also the Cartesian coordinate system, is just a regular X and Y axis system. All right, just trying to pull an image up here. So, all right, so this is the rectangular coordinate system or the Cartesian coordinate system. And just notice there's two axes. We have the horizontal axis, which is x-axis. We have the vertical axis, which is y-axis. We can determine the location of any point in this coordinate system by an ordered pair, right? An ordered pair is in the format x comma y. Well, x would be the horizontal movement and y would be the vertical movement. We also have what is called a polar coordinate system, right? And a polar coordinate system is based on a point called a pole. All right, so here we just have a point, right? And that point is called a pole. A ray is called the polar axis and is usually drawn in the direction of the positive x-axis. Okay? So if you sort of think about an angle, we talked about angles which are in standard position, and angles in standard position, they all begin along this positive x-axis. So when we talk about polar coordinates, okay, we're assuming that all of these polar coordinates are in standard form, basically, if you think about an angle. The ordered pair coordinate of a polar point is in the form r comma theta, where r is the radius, right? The radius is the point from the center to the outer rim, okay, if you're dealing with a circle. And theta is the direction or the angle measure. Here is an example of I'm going to skip a slide, a polar grid, right? So we have a polar grid. So this polar grid is just a series of concentric circles. All right, concentric circles are just circles inside of circles. So notice here we actually have three concentric circles. Right, now this thing can go out further depending upon your value for r. But just notice it's a unit circle. So in our unit circle, I'm just going to bring that up. Notice in the first quadrant, we have 35, we have 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Okay, in every quadrant, we have 3 angle measures. If we take a look at this polar grid, now there is a 45-degree angle. There's just sort of bypassing that 45-degree angle. All right, but this is the unit circle and it's laid out in a polar grid fashion. So notice that this first red circle would have a radius of 1. So for example, if you wanted to plot the point 1, and I actually can't write on this, 1 comma 30 degrees or 1 comma pi over 6, right? We would actually plot that point here, right? So on and so forth. But this is an example of a polar grid, which we had taken a look at in the last class. All right, so now we're going to take a look at the relationship between a rectangular coordinate and a polar coordinate. It says if a point has rectangular coordinates x comma y and polar coordinates r comma theta, then these coordinates are related as follows. All right, so here are the actual formulas that we're using. So we have x, right, and x is a point in a rectangular coordinate system. Its equivalent in the polar coordinate system is written as r times the cosine of theta. Right, so if you're given a polar coordinate, you can convert that polar coordinate to a rectangular coordinate by using this formula. Next, we have that y is equal to r times the sine of theta. Right, so if we're given, for example, 1 comma 30 degrees, we can convert that to an x and y ordered pair point by use of these two formulas. We're also given that r squared is equal to x squared plus y squared, and you should remember this as Pythagorean theorem. Right, so we're dealing with the bottom part as far as the polar coordinates are concerned. So we never really find r squared or use r squared, we use r. Right, so when I go to OneNote in a second, I'm just going to write out r is equal to the square root of x squared plus y squared, which means that if we're given an ordered pair point, right, x comma y, we can substitute x and y into this formula and we can actually find r. We're also given that the tangent of theta is equal to y over x. So if we're given a rectangular coordinate, we can convert that rectangular coordinate into a direction angle theta. All right, so let's take a look at some examples. All right, so I'm going to bring up OneNote and flip around the computer. All right, so here are our formulas. We have x is equal to r cosine theta. Y is equal to r times the sine of theta, and it's trash day, so the truck that you're hearing is in front of the house. All right, so this is for the rectangular coordinate system. Right, so if you're given an x, well, I'm sorry, this is for the polar coordinate system, right? So if you're given an r and a theta, you can actually find x. And then here we have r is equal to the square root of x squared plus y squared. And we have theta is equal to the arctangent of y over x. And these are for rectangular coordinates. Okay. So notice I am writing the formulas quite differently that are on the slide, because for our polar coordinates we want r and theta. All right, so I had taken the first formula, r squared is equal to x squared plus y squared, and I simply squared both sides. I had taken that formula, the tangent of theta is equal to y over x. I simply taken the arc tangent for both sides and out popped the formula for theta. All right, so let's take a look at an example. All right, so in this example, we want to convert to rectangular coordinates. All right, so we're given 2, 5 pi over 6. Right, and we're asked to convert this to rectangular coordinates of x and for y. So since we're given polar coordinates, right, and we want to convert to rectangular coordinates, we're going to use this first set of formulas, right, where we have x is equal to r times the cosine of theta, and that would give us the x coordinate of our ordered pair. And then we have y is equal to r times sine theta, which would give us the y coordinate of our ordered pair. So first, we're going to find x. So we're simply going to use that formula. X is equal to r times the cosine of theta. And we're going to substitute r for 2 and theta for 5 pi over 6. Right, so I'm just simply going to substitute. So I'm going to substitute r for 2, and I'm going to substitute theta for 5 pi over 6. Right, so I'm going to bring down 2, and next I'm going to find the value for the cosine of 5 pi over 6. There's a couple of ways we can find the cosine of 5 pi over 6. We can use the unit circle. So I'm going to go back. I can locate 5 pi over 6, right, which is 150 degrees. Cosine would be the x coordinate, right? So I have negative square root of 3 over 2. I could also, right, I'm going to go back to the formula section for a minute, and I could use this unit circle function value chart. Right, I could find 5 pi over 6, which is here. I can also find the cosine value of negative square root of 3 over 2 by using this function values chart. So I'm going to go back and I'm going to substitute with negative square root of 3 over 2. Right, the 2's are going to cancel, so we have the x coordinate as negative square root of 3. Right, I'm going to find y. Right, so we're going to write the formula. Y is equal to r times the sine of theta. So here again, we're going to substitute r for 2 and theta for 5 pi over 6. So we have 2 times the sine of 5 pi over 6. Right, so we can either use the unit circle or we could use the function values chart. So by doing that, you should see that the sine of 5 power 6 is 1/2. All right, 2 times a half, our 2's cancel, so we have a y coordinate of 1. All right, so the polar coordinate 2, 5 pi over 6 has the equivalent rectangular coordinates of negative square root of 3, 1. All right, so that is the hand method. Now we can also do this by using a calculator, but I must warn you, when you use a calculator, the calculator will never give us an exact value, right? It's always going to give us an approximation. So as you're going through the homework problems, if you're using a calculator and you get an irrational number, a number that never stops, never repeats, it is because you're dealing with a radical somehow, some way. All right, so we'll see how that actually is seen in our problem. So I'm going to bring up the calculator. And I'm going to, okay, there it is. All right, so I'll give you a second to get your calculator if you don't already have it out. Okay, and I'm just going to reset this really quick. Okay. All right, so there are a few functions in the calculator that we're going to be using, and they're located in this angle section, which is above apps on my computer. All right, I mean on my calculator. So I'm going to hit second in apps, which is angle, and we're going to look at the the fifth, sixth, seventh, and eighth formulas. All right, we're actually going to start with 7 and 8. All right, so for our calculator, we have the function number 7, which is p. All right, and then we have r of x. And then for the eighth formula, we have p, and then we have r of y with a open parenthesis. I'm going to kind of explain these two formulas. All right, so what you actually see, the p that you see, it stands for a polar coordinate, right? The r of x, it stands for the rectangular x coordinate. So for number 7, you must input polar coordinates. You must put in r, you must put in a comma, and then you must put in a theta. And it'll give you the x coordinate of your ordered pair. This is to find x given r and theta. The eighth function is to find y, but you have to give it r and theta. All right, so we're actually we're going to check what we just did by hand using the calculator. All right, so I'm just going to slide this back over. All right, so let's find x. I'm going to find x by using the 7th function. Right, so I have to give it polar coordinates, and it's going to give me the x coordinate. So I'm going to hit enter. I'm going to put in, so now here's where you have to be careful. Since we're putting in an angle in radian measure, you want to make sure that your calculator is in radian mode. All right, so now I am in radian mode. All right, so I'm going to put in the polar coordinates 2, 5 pi divided by 6. Right, but notice I'm not going to get negative square root of 3 because the calculator, it's not going to give us square roots. It gives us an approximation. But I could check to see if that's negative square root of 3. Right, so I'm going to put in negative square root of 3. All right, and we have the exact same value. All right, so we have our x coordinate as negative square root of 3. We can also find the y coordinate. So I'm going to go back in the angle. I'm going to go down to the 8th function. All right, I'm already in I'm already in radian mode. Right, I'm going to put in the coordinates 2, 5 pi over 6. Right, and I get 1. So we have converted polar coordinates to rectangular coordinates in 2 ways. We did it by hand by using the formulas, and we also used the calculator. All right, so now we're going to go the other way around. All right, we're going to be given rectangular coordinates, and we want to convert to polar coordinates. All right, so we're given the rectangular coordinates 2, 1. Right, so the first thing we're going to do is find r. So there was a formula for r. R is equal to the square root of x squared plus y squared. We're going to substitute x for 2, and we're going to substitute y for 1. So we have the square root of 2 squared plus 1 squared, right, which is the square root of 5. So we have r is equal to the square root of 5. And next we want to find theta. So we have the formula that theta is equal to the arctangent of y over x. So again, x is 2, y is 1. So we have the arctangent of 1/2. Right, so I am going to use the calculator. So here again, we want to make sure that we are in radian mode. So I'm going to put in the arctangent of 1/2, and we have 0.4636. All right, so we have converted the point 2, 1 to polar form as square root of 5, comma, 0.4636. All right, we can also use the calculator to check our work. So I'm going to go back into angle, and here we're going to concentrate on the 5th and the 6th functions. Okay, so number 5 is, you have to give it rectangular coordinates, so that's what the R stands for, and then it will give you the radius. 6 says if you input rectangular coordinates, it will give you the angle measure. All right, so 5, it gives, we can find R given X and Y. And for the 6 function, we can find theta given an X and a Y. So I'll give you a second to write that down. And then we're going to use the calculator to check. All right, so let's look at finding R. Right, so I'm going to use the 5th function. I'm going to put in 2, 1. All right, now here again, since our answer contains a radical, it's not going to give us the radical, but we can check our work. So I'm going to put in the square root of 5. All right, and we have R. All right, next we're going to find theta. So I'm going to use the 6th function. I'm going to put in 2, 1. All right, and we have theta. All right, so we have taken a look at converting polar to rectangular and also converting rectangular to polar. Okay, next we're going to take a look at polar equations. And I'm just going to go back to XYZ for a second. All right, so we've taken a look at how to graph in the previous section. And okay, I don't know what's going on. All right, so we're in 4.3. All right, we've taken a look at converting from rectangular polar and polar to rectangular. Next, we're going to take a look at equations. All right, so we do have some formulas for our equation. So here we're given a rectangular equation, x is equal to 9. We want to convert that to a polar equation. All right, so I'm going to go back to OneNote. we want to convert to a polar equation. Okay, and we have x is equal to 9. All right, so remember that we do have some formulas, right? We have the formula for x is equal to r times cosine theta, y is equal to r times the sine of theta. Okay, I'm going to just go back for 1 second. Okay, let's just talk about what a polar equation looks like before we actually convert from one to the other. Okay, here we see this first bullet points. It says that here is some examples of polar equations. Now, when we talk about rectangular equations, they have the variable x and y. For polar equations, we have the variables r and theta. A polar equation is usually solved for r. So here we have some examples. We have this first polar equation as r is equal to 3 times the sine of theta, right? So that's an equation, a polar equation, right? It's solved for r. Notice that there is no x and y, right? We only have r, cosine, and sine. Here we have the second example of a polar equation. R is equal to 2 plus cosine of theta, right? So notice here again, our equation is solved for r, right? And we have a cosine. Or we can have an equation such as r is equal to theta, right? But you must have an r, you must have a theta. In some equations, you would have both a sine and a cosine. All right, so here's some examples of polar equations, right? They don't contain x, they don't contain y, and they're solved for r. All right, so let's take a look at an example, right? We want to write this rectangular equation, x is equal to 9. We want to write it in polar form. So when you're converting from rectangular form to polar form, and even vice versa, we're going to use these sets of formulas. Wherever you see an x, you want to rewrite x as r cosine theta. Wherever you see a y, you want to write it as r times the sine of theta. And then you want to solve for r, right? So here's how it works. So we have the equation x is equal to 9. So I'm going to convert, just erase this for a second. So I'm going to substitute x for r times the cosine of theta. Right, so I'm going to write this as r times the cosine of theta is equal to 9. Next, I'm going to solve it for r. So the opposite of multiplying r by cosine of theta is to divide by cosine theta. So I'm going to divide both sides by cosine theta. So once I divide by cosine theta, the cosine theta cancels on the left-hand side, which leaves r. I'm going to divide the right-hand side by cosine theta, and this is our equation, right? Our polar equation, right? So now we're going to take a look at another example. All right, so here again, we're converting to polar equations. We have y squared is equal to 4x. right? So we're going to substitute x equal r times cosine theta, and we're going to substitute y for r times the sine of theta. All right, so we have y squared, so that's r times the sine of theta, right? Quantity squared. That's equal to 4 times x, so we're going to substitute x for r cosine theta, right? So we're going to solve for r, but before we solve for r, we're going to use the order operations. So on the left-hand side, we're going to evaluate the exponent. So I want to bring up a rule from algebra. And it says that a times b to the nth power. So here we're taking a product and raising a product to the nth power. That's going to equal to a to the nth power times b to the nth power, right? So we have to take both factors and we raise both factors to the nth power. All right, so comparing that to the left-hand side, we have r times the sine of theta, right? So we have a product. So we have to raise both factors to the second power. So we have to take r, which is the first factor, we raise that to the second power. We also take the second factor, which is the sine of theta, and we raise that to the second power as well. All right. So we have r squared times the sine of theta squared. On the right-hand side, we have 4 times r cosine theta. So once we multiply or distribute, we have 4 times r cosine theta. All right, so now since there is no plus, right, we don't distribute 4. All right, we simply multiply 4 by the quantity r cosine theta, and we have 4 times r cosine theta. All right, so we have removed the parentheses. Now we need to solve for r. So in solving for r, we need to put r on the same side of our equation, right? So if I look on the left-hand side, I have r squared times sine squared theta. On the right-hand side, I have 4 times r cosine theta. I'm going to move my r's to the left-hand side. So this is how I'm going to do it. I'm going to divide both sides by r. So I'm going to divide the left-hand side by r. I'm going to divide the right-hand side by r. When we divide the left-hand side by r, we get a reduction for r, right? Because r squared divided by r gives us r, right? Because this r is going to cancel out one of the r's in the numerator. So on the left-hand side, we now have r times the sine of theta. On the right-hand side, the r's are going to cancel completely. So we're left with 4 times the cosine of theta. Right, so we've divided both sides by r. Now we're going to solve for r. So the opposite of multiplying r by sine of theta is divide by sine theta. So if we divide both sides by the sine of theta, we have r is equal to 4 cosine theta divided by the sine of theta. Right. So once you substitute x for r cosine theta, and once you substitute y for r times the sine of theta, then there comes some algebra in solving for r. And then there was also problem number 10. Okay. And I'm actually going to do problem number 10. Problem number 10, it was like the only problem in which it was not solved for r. Okay. And I believe the reason why it wasn't solved for r was because the amount of parentheses you would have to put in order for the problem to come out correct. Right? So here's what I mean by that. All right, so like in each one of these problems, let's see, we work this out as, what was that? 9 divided by cosine theta. Okay, 9 divided by, and I have to flip my screen around. And this is one thing I did not like about this section, is actually putting these things in. 9 divided by the cosine. And I'm going to put in a parenthesis. And in order to get that theta, you actually must write out theta. And what did I not do on this? I did not put in r equals, I believe. All right, you got to put in r equal. Right, for problem number 10, this was the only problem in where you actually didn't solve it for r. Okay, but when you write out a polar equation, they must all be solved for r. I'm going to contact the publisher, but I believe the reason why when you write this one out is not solved for r is just because the amount of parentheses you got to keep up with in order to get the problem correct. Okay, so this problem is a little bit unusual, as it actually solves it for, I believe, sine or something to that effect. But we're going to work out this particular problem. It says y is equal to 2x squared. Okay, I'm going to flip the screen around. Hopefully this doesn't knock out on me. Okay, y is equal to 2x squared. All right, so same setup. We're going to substitute x for r cosine theta. We're going to substitute y for r sine theta. So we have r sine theta is equal to 2 times r cosine theta squared. I'm going to remove the parentheses on the left-hand side. So I'm going to bring the right-hand side, I'm going to remove the parentheses on the right-hand side. So I'm going to just simply bring the left-hand side down. And once we simplify the right-hand side, we should have 2 times r squared cosine theta squared. All right, so I evaluated the exponent. Right, and now I'm going to remove the parentheses. So we have r times the sine of theta is equal to 2r squared cosine theta squared. I'm going to divide both sides by r. All right, so we have sine theta is equal to 2r cosine theta squared. All right, and for whatever reason, when I worked this out the first time, there was like a cube there. All right, but problem number 10 is a little bit different, and this is actually what it wants as the final answer. But I'm going to make sure on the test that your polar equation, it should be solved for r. All right. So let me just double check that because it did change up the problem. I'm just going to put 0 in. Right, see, for some strange reason, it doesn't solve problem number 10 for r. All right, it just sort of leaves it in this form. Okay, but if you wanted to go further, you can write this as r is equal to the sine of theta divided by 2 cosine theta squared. Okay. Or you can just divide both sides by 2 cosine theta squared. All right, but this should be the way it should be answered. All right. All right, so we've taken a look at how to convert polar coordinates from rectangular to polar. We've taken a look at how to convert equations from rectangular to polar. Now we're going to take a look at polar graphs. All right, so before we actually take a look at polar graphs, I am going to just pull up Google for a second and just going to look at types of polar graphs. And here are the different types of polar graphs. Only a few are mentioned in our particular section. We have polar graphs that are called cardioids. We have limicons. We have lemon skates. We have rose curves and Archimedes spirals. Right, and these are all different types of polar graphs. Okay, but I won't really get too deep into all of each type of curve. In this course, we are concentrating on cardioids. This is just an example of a cardioid. You notice it's like a heart-shaped sort of graph. We have limicons. All right, so here's some examples of what limicon graphs looks like. Right, and here are the equations that produce limicons. They can be in this form: a plus b times the sine of theta, a plus b times the cosine of theta. They can also be in the form a minus b times the sine of theta, a minus b times the cosine of theta. Right, and it says the ratio a over b determines the shape. This is just some information about what these graphs looks like and what determines them. But in our for our purposes, we're only going to graph them. Okay, we're not going to be asked to describe the shape or anything. Okay. So next we have rose curves. So just notice what the rose curves looks like. They look like rose petals. And if you look at the top of the slide, it says that the rose curves are in this form. R is equal to A times the sine of n times theta, and R is equal to A times the cosine of n times theta. Where if n is even, right, the rose has 2 n petals. If n is odd, the rose has n petals. All right, so here's just some examples of equations and also the graphs for those equations. All right, so how do you graph a polar equation? Now, we're not going to graph anything by hand, but if you had to graph a polar equation by hand, this is how you would do it. Right? In this example, we're asked to graph 1 plus the cosine of theta. Right? So notice when you graph an ordered pair point, you have an X and a Y ordered pair table, right? Where X would be the number you input and Y would be your equation. For polar coordinates, we have R and we have theta, right? Theta is our angle measure, right? And theta comes from the unit circle, 0 degrees, 30 degrees, 45, so on and so forth. R is our polar equation, right? So R in this case is equal to 1 plus the cosine of theta. So instead of an X and a Y chart, we have a theta and an R chart, right? So we simply plug in the degree from the unit circle and it corresponds to a value R, and that polar point is plotted. So we take a look at this first polar coordinate, right? We have 0 degrees, and if you were to substitute 0 degrees for theta, right, the cosine of 0 degrees is 1, right? And we can verify that on the unit circle, right? We have the cosine of 0 degrees is 1. We can look at the x coordinate. We can also look at the function values the function values chart. We have 0 degrees and its cosine is 1. So we have 1 plus 1, which is 2, and that gives us our first ordered pair, 0 degrees, comma 2. And that can be plotted, right? We talked about plotting points. So if we take a look at a graph, first we would find 0 degrees, which is here. And then we would go out 2 spaces. So notice that this thing goes in half spaces. So we have a half, that's our first concentric circle. Then we have 1, which is the second concentric circle. Then we have 1.5, which is the third. And then we have 2, which is actually that fourth concentric circle. So we have the point 0 degrees or 2 comma 0, right, which is actually here. Next, 30 degrees was substituted into for theta. So we can find the cosine of 30 degrees. We can add 1 to that. We get 1.9. And then we can plot the polar coordinate point of 30 degrees, comma 1.9. So we would find 30 degrees, which is here, right? We would find 1.9, which is here, and we would plot that point. Right? And then this would keep going around and around, and then we would have the graph of this cardioid. Okay. But what we're going to do is use the calculator to graph. All right, so we're going to just graph the same equation using the calculator. All right, so I'm going to turn it on. I'm gonna just clear that out. And I just have to make sure that my calculator is in radian mode. Now, one thing about your calculator, unless you physically go in and change this, from degree to radian, you don't have anything to worry about. But since this is a virtual calculator, it'll reset itself at any point in time. So I'm just kind of paranoid about going in and just making sure I'm in the right mode. All right, so when you graph these polar equations, you want to make sure that you are in radian mode, right? You also must go to function, and then we have some options. We have function, F-U-N-C-T, which is function. We have PAR, which is parametric, and we have POL, which is polar. And we want to change from function to polar. All right. So now if we hit y equals, we're going to see something a little bit different, right? Before in y equals, when we were in function mode, we seen y sub 1, right? And we put in the equation, right? Solve for y in terms of x. Once we change our mode to polar, notice we have r sub 1, r sub 2. Okay. So that's the first difference, right? A polar equation must be solved for r. So I'm going to put in the equation 1 plus the cosine. So now where is theta, right? The key we were using before for x, since we've changed the mode on our calculator, if I press that key now I get theta, right? So I'm going to close off the parenthesis. Now, when you graph, you're going to see me toggle between these two things. And my screen is freezing again. Okay, my screen appears to be freezing. But we're going to toggle in between zoom. I'm just going to hit zoom for a second. We're going to toggle in between zoom decimal, zoom standard, and zoom fit. Okay, so we have to play around with these graphs a little bit in order to get the full shape sometimes. So that's zoom decimal. So if you hit zoom, zoom decimal is the 4th option. Zoom standard is the 6th option, and zoom fit is the 10th option. All right, so I'm always going to start off using zoom standard. And let's see, why does my graph look like this? Okay, for whatever reason, I should not have that. Let me delete that. All right, so I'm going to use zoom standard. Okay, notice the graph looks like that. I can use zoom decimal. So I'm going to hit zoom decimal. And I get a better look at the graph. And it looks like, what I'm looking on the slide. I can also hit zoom and 0, which is zoom fit. Okay. All right, so notice you may have to toggle between those 3 things, right? I believe you can also use zoom standard. Let me just try that. Zoom standard. Okay. All right, so zoom standard, it makes it appear in a rectangular. It's close to the graph, so let me just write that down. That was zoom standard. Okay. Because in this section, we're basically going to have to match our calculator with the answer choices. All right, so let's take a look at X, Y, Z. And I believe this is actually in the next section. 4.4. All right, so let's take a look at number 1. All right, we're given we're given R is equal to 5 cosine theta, and we're given 4 graphs to choose from. Right, so I'm going to go to R to Y equals. Right, so notice now in mode, we want to make sure we're in radian mode. We also want to make sure we're dealing with polar equations. I'm going to put in 5 cosine theta. I'm going to hit zoom 6. Right, I'm always going to start with zoom 6. Next, I'm going to use zoom square. And I'm sorry, that should be zoom square. Okay. All right, so I can pretty much determine that, right, this is my correct answer choice. All right. All right. All right, so we get D. All right, we'll take a look at some more examples. All right, this is number 4. All right, we're given 7 minus 6 times the cosine of theta. All right, so here again, there's nothing to graph by hand. Right, we're simply going to use a calculator, but you do have the knowledge to graph it if you wanted to graph by hand. I'm going to go into Y equals, and this is 7 minus 6 times the cosine of theta. Right, I'm going to use zoom 6. All right, so notice carefully our last 2 answer choices, they look similar, right? One has that's called an inner loop. Okay, and then one has a cardioid shape. I believe we should have this as the correct choice. Okay. All right. So I believe they have some rose petals on this thing. Let's see. All right, let's take a look at number 10. All right, we have R is equal to 4 times the cosine of 2 theta. All right, so I'm going to just put that into R equals as 4 cosine 2 theta. I want to hit zoom 6, which is zoom standard. And I believe we should have that as the right answer choice. All right, and that is called a rose curve. All right. Okay, now here's one you got to pay careful attention to. This is problem number 12. All right, so notice, and I did not quite point this out on the last couple of problems. All right, notice for number 12, they give us this interval from 0 to 3 pi, right? So if I were to just graph r is equal to theta, I'm going to go into y equals, I'm going to clear that out. I'm going to go into r is equal to theta, right? And I'm going to graph. All right, so notice that is not one of my answer choices. And here is the reason why. For the polar graph, the default, I'm going to go into window for a second. The default is usually from 0 to 2 pi. So I have here my theta minimum is 0. Okay, we have some other stuff in here. We have like theta step and x min, x max. That's x min, x max, that x min and x max, that sort of thing. But we have theta max is 6.283. Now the 6.283, that's actually 2 pi, right? That's 6.2831. But notice that our interval is from 0 to 3 pi, right? So I'm going to go in the window and I want to change my theta max to 3 pi. And now I want to graph. All right, so our correct answer choice should be the first one. All right, I just wanted to point that out because by default, the interval on the calculator is 0 to 2 pi. So if you're given anything other than 2 pi, you want to go in the window and you want to make your adjustments. Now we have two more. There's number 13 and there is number 14. All right, so let's take a look at 13. Okay, now this says draw each polar equation on the same set of polar axes, and it wants us to find the intersection. All right, and it wants the intersection from 0 to 2 pi. So I'm given, and I'm going to write this down. R sub 1 is equal to 3 minus 4 cosine theta. R sub 2 is equal to 1. All right, so I'm just going to graph both of those. I'm going to graph 3 minus 4 times the cosine of theta. And I'm going to graph R sub 2 is 1. Okay, I'm going to hit zoom 6. And I am going to hit zoom fit. So I'm going to hit zoom 0. All right, and it should fit the graph to our screen. Okay. And we're looking for the intersection points from 0 to 2 pi. All right. And I wish I could actually blow my calculator up. Let me see if I could do that. All right. All right, so we want the intersection from 0 to 2 pi. So notice that the rectangular coordinate system itself, all right, we're going to treat that as a unit circle. So here we have 0 degrees, All right, here we have 90, 180, 270, back to 360. Let me just go down. All right, so notice these two graphs, they intersect here. And they also intersect here, right? So we actually want these two ordered pair points. All right. And I'm going to shrink this a little bit. I'm going to go into y equals, and I'm going to turn the first graph off just to show something for a second. All right, so in order to turn a graph off, you would simply go to the equal sign. You would hit enter to de-highlight the equal sign. And now if I graph, it's only going to graph the highlighted equation. I want you to realize that this second equation, r sub 2 is equal to 1, that's nothing more than a circle with a radius of 1, right? So if I were to hit like zoom decimal, that's just a circle with a radius of 1, right? So now I'm going to go back to r sub 1. Right, I'm going to highlight it so it'll graph, and now I'm going to just put both graphs together. All right, so we're looking for these 2 points of intersection. So I know that my x coordinate should be 1, right? Because I would have to go 1 unit to the right, and then I would go up. I'm going to have to find the y coordinate. And then in order to find this other intersection point, I would go, I'm at the origin, I would move 1 unit to the right, and then I would go down. All right, so let's take a look at finding the y coordinates. All right, so I'm going to go back to OneNote and put my screen on. All right, so I'm going to take those two equations. I have find the points of intersection. So we have r sub 1 is equal to 3 minus 4 times cosine of theta. We have r sub 2 is equal to 1. So now if we were dealing with rectangular coordinates, we would just set both equations equal and solve. That's the same thing we're going to do here. I'm going to take both of these equations. I'm going to set them equal, and I'm going to solve, in this case, for cosine. Right? So I'm going to, first off, subtract 3 from both sides. So I have negative 4 cosine theta is equal to negative 2. I'm going to divide both sides by negative 4. So I have cosine of theta is equal to 1/2. So remember, from solving trig equations, I'm going to interpret this as what angle in the interval from 0 to 2 pi has a cosine, which is x value, of 1/2. Right, so I'm going to look in the unit circle. All right, So I'm going to look for two angles that have an x coordinate of 1/2. So I see that pi over 3, right? It has an x coordinate of positive 1/2. I also see that 5 pi over 3 has an x coordinate of 1/2. Right, so theta is equal to pi over 3 and 5 pi over 3. Right, so we've already determined, since r sub 2 has a radius of 1, our 2 points of intersection should be 1 comma pi over 3 and 1 comma 5 pi over 3. I'm going to see if... Okay, now one thing, there is no calculate. Like if we were dealing with rectangular coordinates, we can do a calculate and then we can find a point of intersection. But I believe I can do a trace. And I'm going to blow this up slightly. So let's see. I'm going to go to zoom box. And I'm going to make a box. Okay, just around this piece. And it should just blow that up. All right. I'm going to hit trace. And I believe it's going to allow me to trace. All right, so if I look at this intersection point, I have 0.5, and I have my y as 0.8660245. I believe this should be pi over 3. Oops, pi over 3. Oh, let me go back into... Hmm. 1.047, y is... Okay, I want to go back to the home screen. Okay, I don't know what's okay. 1.3. So 1.043. Okay, that's my pi over 3, right? 1.047. Okay, I lost it. So I'm gonna go back in the trace. So that's the 1.047. And then if we go down to go down. Okay, I think I may have to go all the way around the... Okay, there it is. All right, and then we have this intersection point as 5.235. And that should be 5 pi over 3. Pi divided by 3. And I have no idea what's going on with my calculator. All right, but we should have these 2 points of intersection. So that should be, I'm going to go back to 1 comma pi over 3. And 1 comma 5 pi. All right, so we have those 2 points of intersection. Okay, my calculator was acting kind of quirky, but all right. And problem number 14, we're out of time, but problem number 14 is similar. You can graph both on the same graph. You can find that point of intersection, and we will take a look at this one on the next session. All right, so here I'm going to stop the recording.